Okay, chemists, we're going to keep talking about kinetics in this lesson. The last time we talked, we looked at what are called differential rates. Differential rates show how rates change with concentration. Because we wrote things like rate equals k times the molarity of something to some exponent. And remember, that was a change in molarity per change in time, or really a change in amount. That's fine. However, when you go to the laboratory, we don't often have a way of measuring rate. I don't have a rateometer. I have ways of measuring time. So today I'm going to teach you how we look at what are called integrated rate laws, and these show how concentration change with time. They're actually related to the differential rate laws, and they vary depending on what the order of the reaction is. And I'm going to derive the three most common orders that we see for you. Disclaimer, you do not need to reproduce these derivations. I'm just going to show you the math of where they come from instead of just giving you the equations. The equations are for the most part on your reference table and easily looked up in any kinetics summary box with equations that you use in this unit, but I like to show how we turn this into what are called integrated rate laws, and hopefully it will overlap a little bit with what's going on in your math classes. First, let's go through a zero order process. So a zero order reaction, for some generic reaction, I'm just going to look at some molecule A turning into some molecule B. If it's zero order, I can write a rate law where rate is equal to K times the concentration of the reactants. And if it's zero order, that means the exponent is 0. Well, remember, anything to the 0 power is 1, so this just becomes K. Zero order processes are where the rate is actually constant. The rate does not change with time. Now I'm going to rewrite that word rate as a depletion of reactant. Really, when I wrote that up here, it's really the negative of the change in amount of reactant per time, because reactants decrease as time goes on. So if I write change in concentration of A per change in time and put a negative sign in front of it, that's what is equal to K. Now I'm going to change those deltas to infinitesimal deltas, differentials, and instead of capital delta for some overall, I'm going to make them a differential delta and call it lowercase d bracket a. Now, if you haven't done differential calculus in your math classes yet, that's okay. Just follow along in the meantime. And now I'm going to rearrange some things and move this differential a to be by itself on one side of the equation. And then I get differential a is equal to the negative of K differential T. All I did was take this and rearrange into that equation. And once you have differentials, we can do what's called an integration. So I'm going to integrate the differential of A and integrate the negative of a constant times the differential of T. Those are called integral signs when you do that. Again, if you haven't seen this yet, that's okay. You will see this in your math class. The integral of 1 with respect to A from some final A to some initial A is the change in A. It's A at some time minus A under initial conditions. And that's true for here as well. The integral of the differential with respect to T, and I can take a constant to just put it out in front, is a final T minus an initial T. An initial T I'm just going to call 0. So that just becomes negative K, the constant, times the time, T. And if I rearrange and solve this for A, I get the concentration of A at some time is equal to negative KT plus the original concentration. That's called the integrated rate law for a first order process, and I'd like you to put a box around that. That's our derived rate law. Again, it's okay if you didn't understand everything that happened in that derivation, as long as you take my word for it that that's the equation we get in the end. And what that means is I now have a y equals mx plus b type equation, so I can make a straight line out of this. If I plot the molarity of A as a function of time, it will decrease linearly, and then the slope of this is proportional to the rate constant. It's actually equal to the negative of the rate constant. So what we're going to do is the same kind of analysis for first order and then second order processes and come up with a different differential rate law, or excuse me, integrated rate law for those two processes. So let's look at the same equation for a first order process, A turning into B. This time rate is equal to K times A to the first power, and that's still negative change in amount of A per change in time. I'm using the same thing we did in the first part. The only thing that's different is I now have an exponent of 1. So I'm going to replace those change in A's with a differential. That means I have, I'm going to move the negative sign to the other side. That means I have the differential of A over the differential of T is equal to negative K times A. And now I'm going to move the differentials to 1 on each side. But I'm also going to put this A in the denominator of the left-hand side. That gives me the differential of A all over A is equal to negative KT. And just like before, I'm going to integrate the left and integrate the right. Now, the right looks exactly the same as what I have before. So the right-hand side of this still becomes negative KT. Whoops, this was actually dt, wasn't it? Negative K dt. The integral of negative k dt is negative kt. Here I have the integral of 1 over a with respect to a, and that turns into the natural log of a for reasons that I'm not going to go into in this class. See your math class for more information. But that means I'm going to have the natural log of a minus the natural log of an initial a. It's always boundaried from t0 to some t. And if I rearrange that, I get the natural log of a is equal to, it'll be negative k t plus the natural log of effectively a constant, whatever my initial concentration is. And that's your first order expression. So as time varies, concentration versus time is not linear, but the log of concentration versus time is linear. So on the y-axis, I'm not going to plot concentration, I'm going to plot the log of the concentration, and that will give us a linear relationship where the slope is once again proportional to k and equal to negative k. So there's only one left in terms of the most common types. Zero order is concentration versus time. First order is log of concentration versus time. Let's see what second order is. Second order, we still have rate is equal to k times concentration, but this time to the second power. That means if I have negative d concentration dt, that's going to be equal to k times bracket a squared. So now I'm going to have 1 over the concentration of a squared, differential a, is equal to negative k differential t, and I integrate both sides. Once again, the right half is the same, left half is different. I'm integrating 1 over a squared. That becomes negative 1 over a, and then you subtract it from initial conditions, and once you rearrange and solve, I'll just cut to the chase, you get 1 over concentration of A at some time is equal to positive KT plus 1 over concentration of A under initial conditions. Going through that quickly because it's not too important for this stage of the class to know where these come from, but for some of us math fans out there, I wanted to just show you that we didn't just pull them out of thin air. So what does this equation look like? It's not log versus time, it's not concentration versus time, it's inverse concentration versus time. And that'll be a straight line, but also this one's quite different because the slope will be positive. So here the slope is equal to the positive value of K, which means that if I want to go into the lab and study a reaction, I can monitor concentration versus time and graphically determine what the order is. Most chemists do this backwards. We look at 3 different relationships, or as many as it takes, and we study concentration versus time, logarithmic concentration versus time, and inverse concentration versus time. And whichever one is the most linear, that tells us which order the reaction is with respect to that reactant. It's actually a very complicated process. It takes a lot of data collection, but that's how you get it. In fact, you're going to do this in the lab as well in this class and study a reaction and look at how it changes with time. So let's look at an example problem, and then we'll wrap up with another way we talk about rates called half-life. So this one says find the rate constant for a reaction. They tell us that it's first order. Underline that. This is given to us as a first order process. And they measure the concentration versus time, but I know that that's not going to be linear. What is going to be linear is the natural log of the concentration versus time. So the natural log of N2O5 will be a linear relationship. And we can just mathematically get the natural log of all these numbers. That would be negative 2.303 for the first one, negative 2.649 for the second one. I'm just plugging them into my calculator. Negative 2.996, negative 3.689, negative 4.382, and negative 5.075. If I want the rate constant, I need a slope of a graph. So the natural log of the reactant, N2O5, is equal to negative KT plus the natural log of the initial concentration of N2O5. And we can plot a rough sketch of what that would look like here. I'm going to very roughly indicate it, starting in between the negative 2 and negative 3 and getting down to the negative 5 and change, and you'll have a rough linear relationship that looks like that once you plot it. So the slope is negative K, so K is negative slope. So I take the negative of rise over run, and I'm going to do it manually. But I'm actually just going to use the data points in the graph. I'll use the last one and the first one. You should be able to use any two because it's linear the whole time, but I feel like it's easiest just to look at the final numbers and the beginning numbers and then go back and plug those in. So the rise over the run becomes 5.075. Again, it's the logarithm values minus the negative 2.303. And then divided by the run, which is 400 minus 0 seconds. And when you plug that in, you get a magnitude of 0.00693. Apparently a very slow reaction. And I'll just check what my units are. It looks like the time is in seconds. So this first order rate constant will be in inverse seconds. We had some homework problems on the previous unit that practiced looking at what the units were for different rate constants. They depend on the order. All right, last thing. Let's talk about that rate constant a little bit more specifically and show how some chemists define the rate of a reaction by comparing what's called the half-life. The half-life is the time required for a reactant to reach half of its original concentration. So arbitrarily, let's look at the decay of a first-order reaction. Remember, if we go back to our first unit of this, concentration versus time is typically not linear. We just proved that today. It is linear for zero-order processes, but those are pretty rare. For a first order and all the others, concentration versus time is not linear. If it was first order, we would see a decay that looks something like this. It would never hit 0, but if I started at a value of 1, I would get to a value of 0.5 after a certain amount of time. And I'm going to benchmark that time on the x-axis. And then there's some amount of time for this to get cut in half again. So how do I get to 0.25? Well, that's going to hit the graph at some other amount of time. And I could keep going. When do I cut that in half to 0.125? That will cut in half at another amount of time. And you'll notice, I hope you can see in this graph, is that the amount of time, this is not a coincidence, is actually the same. That's what's called the half-life. And it's actually constant for a first order process. It's not constant for the other orders. This is a unique property of half-lives in first orders. They are constant. In fact, I made a note of that up here. The AP asks us this all the time. The first order reactions have a constant half-life. Highlight that for yourself. And we can relate it mathematically using the integrated rate laws that we have up above. So if this is a first order process, we have the equation, the natural log of A is equal to negative KT plus the natural log of initial A. And I'm going to rearrange and solve for KT, move it to the other side. KT is equal to the natural log of initial concentration minus natural log of A at some time. And what I'm going to do is say, well, what time am I talking about? I'm talking about the half-life. So I want to know at the half-life, what's true about the half-life and K? Well, K times T half is equal to apparently the difference between these. Now, if you remember your rules for logarithms, the log of something minus the log of something else is really just the natural log of the quotient, A initial minus A at halfway through. What's true about A as I'm halfway there? Well, what we just graphed is that it's half of whatever it was. So my initial goes down to half of it at one half-life. Or another value goes down to half of it after another half-life. So that means A initial is double whatever A at a half-life is. So I can actually rewrite this as the natural log of A initial over 1/2 of A initial. And that means my A initials cancel. And I get the natural log of 1/2, which is just the natural log of 2. So K, the rate constant, is just a mathematical number, the natural log of 2, divided by the half-life. So half-life and rate constant are always related to each other, and many chemists use half-lives to explain how fast reactions work. This is what's true for a first-order process. This just happens to be the most common one. This is not what it is for the other orders. A good challenge problem is to go back and prove to yourself that for zero order and for second order, it's different. The zero order process would have a half-life that's equal to the initial concentration divided by 2 times K. And the second order process would have a half-life that's equal to 1/K times A initial. They're different. Good challenge problem is to go just see if you can derive those yourselves, just using the different integrated rate law. Okay, so that was a pretty heavy lesson going through all this math. Again, if you haven't had the calculus, that's okay. I could have just given you these equations to begin with. We use them to graphically determine what the order of a reaction is with respect to a specific substance in that reaction, a specific reactant. And we can talk about how fast reactions are by using the half-lives, which are based on what the order is, and they relate the rate constant to the half-life. Only the first order one is constant, and you'll see some practice with that on your homework.